23 cometary observations from 1337 to 1698 that he realized some of the comets followed a similar trajectory and orbit. He identified the apparitions from 1531, 1607, and 1682, and predicted a return date of 1758-59-ish. Unfortunately, he died in 1742, so he didn't get to see it when it actually did come back in 1759. Consequently, the comet was named after him, which I think is kind of sweet. It was also around this period that Charles Messier was inspired to study astronomy when he observed the famous Great Six-Tailed Comet of 1744. Later, he and Pierre Méchain created the Messier catalog. As comet hunters, they were somewhat frustrated by the fact that they would keep getting sidetracked by objects that were not comets, things like galaxies, nebulas, star clusters. So they listed things that were not comets in the sky so that they could pick out the real things. Meanwhile, astronomers and physicists were also hypothesizing about the composition of comets. Newton figured they were small solid bodies with vapor trails heated by the sun, so points for Newton. In the 1860s, Giovanni Schiaparelli found the connection between comets and meteors when he compared the orbit of comet Swift-Tuttle with the Perseids. As you see, Earth passes through kind of the remains of comet Swift-Tuttle, and that causes the meteor shower. These days, comet research has evolved from purely theoretical to a more hands-on approach, which is quite exciting. So we'll talk about that next. We'll talk about the Halley Armada, which was a group of about 5 space probes. There's 6. I don't know anything about ice, sorry. These were sent to examine Halley's Comet when it came to the inner solar system in 1986. The distances represent kind of closest approach. So Japan came first. These are all actually in order of date too, with Sagigake. And then that was kind of a test for its next, Suisei. And then France and the USSR joined intellectual forces to send up Vega 1 and Vega 2. And then the European Space Agency's Giotto used the data from all 4 previous missions to get as close as 596 kilometers, which is a bit more than the distance from Winnipeg to Regina. Otherwise, it was projected to only get as close as 4,000 kilometers. Moving on to NASA, because NASA always has to have a part. Deep Space One flew by Comet Borrelly in 2001, taking high-resolution images, which were useful for describing the surface of the comet, but not the interior composition. So they began with Stardust, which got within 236 kilometers of Comet Wild 2 in 2004. It managed to collect particles and dust, which returned to Earth in 2006 for analysis, which showed that these comets contained minerals formed near the sun or other stars, which led to the question of how this matter got to the outer regions of the solar system. Deep Impact 1 did both a flyby and an impact of Comet Tempel 1. Its mission, sorry, I said Deep Impact 1, just Deep Impact. Its mission was to find what lay beneath the top layer of soot on the comet, so it created a crater for itself, finding that the comet was indeed mostly ice water below the surface. My favorite was the European Space Agency's Rosetta mission, which was the first time a spacecraft has ever landed on a comet, when its lander touched down on the surface of comet Churyumov-Gerasimenko. It has resulted in some pretty spectacular images. The bottom one was put together by an amateur astronomer, I believe. As for upcoming missions, I could only find really one for China. They've announced plans to explore a small near-Earth asteroid before moving on to the asteroid belt to Comet 133P, or else to Pizarro, which is either an asteroidy comet or a comety asteroid. So we'll get into kind of what are comets. Unfortunately, they don't have a pretty nickname. They're kind of called dirty snowballs. While this doesn't really do them justice in the image, it's kind of accurate. The main ingredients are water, or methane and nitrogen and other those types, but in ice form, and then dirt. And all of these are clumped together in the nucleus of the comet, which is extremely minuscule. You'll probably not find it. It's usually no larger than a few kilometers across. When they cross paths with the sun, though, or they get close enough, they heat up, and their solid, icy material becomes gas without even passing through the liquid stage, really. It just starts immediately outgassing. Outgassing creates a visible atmosphere around the comet. As you can see, the bright parts, called the coma. There. Coma coming from the Greek for hair, because they were just hairy stars to the Greeks. The comet itself can be hundreds of thousands of kilometers across. So they kind of give comets their name. Outgassing also results in two tails, one gas and one dust. There's the gas or ion tail, and there's the dust tail. They're labeled, so I don't know why I did that. The ion tail is visible because the gas gets excited by the solar wind and releases its own energy in the form of light. The tail will always blow off the comet from the side furthest from the sun. As you can see here, the blue one, in this case, actually represents the ion tail, so it's always pointing opposite the sun. The dust tail is visible because of the light from the sun reflects off the particles, and it usually curves in the direction of the sun's orbit, the comet's orbit. These tails can reach extraordinary lengths, as you can see in the bottom diagram. Comets are often mistaken for asteroids or meteors as well, so I want to disprove that because they're not asteroids or meteors, but I can understand why people get confused. For example, comets and meteors are both illuminated, but for different amounts of time. Obviously, meteors are only visible for a very brief moment, easily missed, as it encounters the Earth's atmosphere, whereas comets last much longer, in the order of days, weeks, months, as we showed earlier. Meteors are relatively small compared to comets, where comets can be the size of a small town. Meteors range from the size of a grain of sand to a boulder. And then asteroids differ from comets in their composition, usually rock or metal or both. Because they don't have ice-like materials, they don't experience outgassing, thus they don't get comets when they get close to the sun and do not light up. Most comets come from the furthest region of the solar system, called the Kuiper Belt. Small writing, so it's right there. This is exponential, so it's not a good scale, but it kind of gives you an idea. The Kuiper Belt lies beyond the orbit of Neptune, so around 30 astronomical units to 55 astronomical units. So that's 30 to 55 times the distance from the Earth to the Sun, in case you didn't know. It's a ring of small, icy solar system bodies. Comets from the Kuiper Belt are usually called short period, meaning they have an orbital period of 200 years or less. So we get to see them a bit more often. Theoretically, beyond the Kuiper Belt is the Oort cloud, which is more of a sphere than a cloud, but it is theoretical, so who knows. It's believed it could be the remains of the material that formed the solar system. It would probably start at about 2,000 astronomical units from the sun and reach out as far as a quarter of the way to our closest celestial neighbor, Proxima Centauri. The journey from the Oort cloud is much longer, as you can expect, so comets from here are called long period, which can range anywhere from 200 years to 30 million years. Something to note, though, is that comets rarely follow the ecliptic. So the ecliptic is the solar system. Because they're coming from kind of areas that are not just along the ecliptic, their orbits are different. They do have elliptical orbits, but they're much more elongated than those of the planets, and most comets have a unique orbit, which can be measured by the axis, plane, eccentricity, its location at aphelion, which is the furthest point from the Sun, and at perihelion, which is the closest point to the Sun. And we'll talk more about comet orbits a bit later. So what was the point of all these missions and future missions and the knowledge that they kind of got us? What makes these glorified snowballs worth the time, the effort, and especially the money? Mostly we're interested in what they can tell us about the past. As far as we know, comets have remained nearly unchanged since the formation of the solar system, as opposed to the planets, which have gone through geological and climate changes over the period. So our surfaces at the planets are actually much younger than the planets themselves, and so they can't really tell us as much. So by studying comets, we have a better idea of the early solar system formation and what matter was abundant at that time. Comets also give us clues as to early Earth evolution. When the Earth was still young, about 3.8 billion years ago, Earth was in the period known as the late heavy bombardment from comets and other space debris. Because of the constant barrage, life during the bombardment would have been highly unlikely. But life emerged about 3.5 billion years ago against our expectations. So where did this life come from? Young Earth was extremely hot, very little water, so where did the oceans come from? Scientists believe that comets were responsible for both. Missions have shown that comets contain organic molecules as well as frozen water. So is it possible that the origin of all life on Earth came from these comets? Scientists are also interested in future applications of comets. During future space missions, comets could be mined for water. Liquid and hydrogen are ingredients found in comets, and they're also ingredients in rocket fuel. And yet, with all these promising results, we'll also have to keep in mind that comets are possible threats. Given their sizes, many believe a comet colliding with Earth could cause an extinction-level event. Others believe, perhaps optimistically, that comets would just burn up in the atmosphere. So if you're worried about nightmares, just keep that in mind. Comets share many similar properties and origins, but they also distinguish themselves from each other in a number of ways. For example, orbits. Comets that have closed orbits, are called periodic comets because they visit periodically. Right? A periodic comet will be denoted by a slash. Once it's been observed to pass perihelion twice, it gets a number showing the order of discovery. So Halley was the first. Churyumov-Gerasimenko was the 67th verified periodic comet. Non-periodic comets are comets that have only been observed at perihelion once, or only once in over 200 years. These comets are denoted by a C. If you're wondering what the numbers and the letters after the slash mean, 2007 was the year the comet was first discovered. E represents the half month it was discovered, so it's the fifth letter in the alphabet, fifth half month, followed by a number designating the order of discovery. In this case, Comet Lovejoy was the second comet discovered in the first half of March 2007. A subset of non-periodic comets are aberrations, comets that only visit our inner solar system once before flying out into this interstellar space. They follow a parabolic or hyperbolic orbit around the Sun. This usually only happens because comets have interfered or been interfered by other solar system objects like Jupiter. Sometimes we know that comets are for sure not periodic though, because we're lucky enough to know what happens to them. After so many passes around the Sun losing material, eventually there is not enough to form a coma, so it goes dark. These are dormant comets, a comet in which most of the volatile material has been exhausted, leaving just a dark, inert piece of rock, not dissimilar to an asteroid, which is how you can have a comety asteroid or an asteroid comet. Another fate for a comet is to break apart due to heat, impact, or internal pressure from the gases inside. These are usually more spectacular, like in the case of Schwarzmann-Walkman in '95 or Shoemaker-Levy 9 in collided with Jupiter in the first directly observed collision between two extraterrestrial objects that we directly observed. If you see a comet with a D/ in the name, it's because it's died, but there aren't that many. As you can see, even though Swashbuckling Walkman died, it still has a P in front of it. Then we have sun grazers, which are comets that pass within 850 miles of the sun, though some pass as close as a few thousand. There is a group of sun grazers that follow a similar orbit called Kreutz, called the Kreutz path, and so they are collectively dubbed Kreutz sun grazers. It's widely accepted that they were all part of one large sun grazer, which broke apart hundreds of thousands of years ago, hundreds or thousands. Lovejoy is one such sun grazer, and so far the only one we know of that survived its recent close encounter. But another thing is to consider is that comets are not exclusive to our solar system. So cosmic bodies called exocomets are comets that are beyond our solar system. As of 2013, which I know is kind of ways back, 10 exocomets have been observed orbiting other stars. So, do other solar systems have their own Kuiper belts? Do they have their own Oort clouds? And most especially, if comets are harbingers of life and water, does that have implications for extraterrestrial life? So now I'll talk a little bit, briefly, unfortunately, about how to observe. Naturally, this section is geared towards non-auto-guided telescopes. I don't use an auto-guided telescope myself, so that's how I know. As with most observing, it is helpful to know the night sky before you go out trying to observe something special like comets. Messier's logic is sound. Comets are very similar to other faint fuzzies, so it can be difficult to distinguish. That's why it's helpful and important to know what you're looking at is not something else. It saves face if you accidentally show someone who knows that you're full of it. It's also helpful because comets are not static relative to the sky. If you know what's staying still, then you know what's moving, and therefore you can observe comets. If your goal is to discover a comet, it's good to start by observing known comets. So that's where we'll get started. Observing comets is not really like observing faint fuzzies, in my experience. Another universal tip for observing that applies to comet observing is to know your resources. If you're not sure where to start, I would highly recommend the Observer's Handbook. It's included in subscription, but I hear you can buy it somewhere as well. It comes out every year, so you can be sure the information is up to date. This year's section on comets was just 4 pages long, so it's really quick and easy to read. But I really like that it lists notable comets for the current year. Comet magnitudes are notoriously difficult to predict, so they try to get the comets that they expect are going to reach magnitude 18 or greater. The table gives a few statistics meant to help you get an idea about the comets. Critically, when the comet reaches perihelion, its closest point to the sun, when it's likely to get brightest. The handbook also gives an idea of what comet hunting is like. Some tips for both visual and photographic comet hunting, as well as some information about comets. It has some suggestions for further reading, like David Levy's Guide to Observing and Discovering Comets. Great resource, it's very knowledgeable. So it really is just a quick introduction. But if you want a fast way to see if there are any comets coming up, you can look it up on the table and do some more research from there. It's really just a start. Then once you know what you are observing, you can look it up elsewhere, either your preferred planetarium software or elsewhere in the internet. It's critical to get the position of the comet at the correct time as they move. So, yeah. Another resource that I liked was heavensabove.com. It does have a section on comets, and the page will show the brightest current comets of the month. Really small, you can fit it all in there. But yeah, just trust me. Websites like this give helpful information, both visual and textual, to help you find a comet on a specific date at a specific time. I found personally that the site wasn't particularly user-friendly, because I looked in the handbook, found comet linear neat, and So I just Googled heavens above, linear neat, and it brought me to that page. So just use creative means, I guess, or the most obvious solution. Yeah, so it gives you something like this, and then if you want, you can use this in conjunction with other star charts. It's kind of faint. You can actually see that's Leo, so it shows you like where it would be at. Gosh, what time? I don't know. At some time. Finally, any good comet will be visible with a good pair of binoculars, or even a small telescope. You don't need anything extravagant to see the Messier objects, and comets are fairly similar in that respect. So bigger telescopes might get you more definition, but are not strictly necessary, which is good news for most beginner astronomers. Some comets, like the great comets though, will be visible naked eye. That's the exception, not the rule. There's usually about 1 or 2 great comets every decade. So you do have something like this to look forward to, hopefully in your lifetime. If you're looking to make a new discovery, however, you'll have most luck with deep, clear, dark skies. As with any faint fuzzy light pollution is an ongoing concern. You'll also want a clear view of the horizon. You have to remember the nature of comets. They are most visible when closest to the sun, so you'll have a better chance looking for comets on the horizon to the east shortly before sunrise, or to the west shortly after sunset, just like you would observing Mercury or Venus. Something to remember about this, though, is that comets do not necessarily stick to the solar system's ecliptic, so you want to sweep the whole horizon. But observing close to the horizon also comes with its own risks, namely the sun, so make sure you're looking after sunset. But also, you'll want to check the weather in particular, because being so close to the horizon, you're looking for more atmosphere, as you would if you were looking through zenith. So you'll want clear, calm skies as much as possible. If you're looking to get into the comet hunting game in earnest, I'll warn you that it does take long hours and patience. I don't speak from experience, unfortunately, or fortunately, rather. But that was kind of a recurring theme in all of my readings, is there are some people who get lucky. I think one person discovered a new comet after 3 hours, 3 nights or rather, of observing. That's the exception, not the rule. It's getting harder and harder these days. There's more amateur astronomers with even better equipment, so competition is quite fierce. And you're also competing with massive projects that are constantly staring at the sun, like SOHO, and so yeah, you really need to have a lot of time and patience. But if you do decide to go for it, you certainly won't be disappointed, and I hope now you know kind of what you're looking at.
Next up, we're going to have Aaron. Just super quick, I'm just going to talk about our mentorship program. Awesome talk, Aaron. By the way, if anybody else wants to do a beginner's talk, let Brian or myself know so we can schedule in. We'd be happy to have somebody at that for you. When you want to do a talk?
Your mic is not turned on.
It isn't turned on? Oh, okay. There, now it is, right? I think so.
Let's try it now. I'll say that again. If anybody wants to do a beginner's talk, by all means, just let either Brian or myself know. We'd be happy to have you come out. And it also gives me a little break too, which is kind of nice once in a while. So I know most of you have heard this, but I know we have a few people that haven't been in a while, so I just wanted to super quickly just mention our program here. Good. Okay, mentorship program for those that are new observers. So we have, what we've done here basically is we're trying to get people who are new in the hobby to get the help they need. And we're definitely, I'm sort of taking the lead on this for a lot of extracurricular type of observing sessions. We've had 2 so far, but we're going to have about probably another 3 or 4 before the star party, ideally, if we can, weather permitting, of course. One of them was going to be kind of tied into Brian's thing this week. We'll talk about this, but I think the weather's going to be a bit varied. Anyway, the idea here for the mentorship program is basically just to help people get help with their gear, getting set up and learning the sky, asking lots of questions and so on. So these are some of the topics that we normally talk about on this. Myself, Brian, and Bill Crosby, who's not here tonight, normally are the mentors, but if anybody wants to volunteer, let's say if we have a session going on, by all means just let us know, and we'd be happy to have you come on board and help out. Often people will be setting up new scopes, or maybe they're having trouble finding something, or maybe they're trying to align their polar scope or something and they're just having an issue. It's really helpful to have people out helping these folks. I wanted to mention about Brian will mention this a little bit too, but what I'm going to do at one of our events here, we're going to do what's called the Solstice Solar Session. I was actually talking to Sylvia just before we started tonight. I think we might move it to Sunday instead of the 22nd. I think we might do the 23rd. I'll make an announcement on it. It'll hinge on the weather as well as a few other things, but the moon will be setting a little later on Sunday rather than the Saturday. So we're going to tentatively do it around 10 o'clock or maybe between 9:30 and 10 if people want to show up. And then we'll do about 4 or 5 hours of solar observing. So whoever does have solar equipment, we'll have our Club PST out. I'll have a couple of solar scopes out as well, including my HL to set up. And if somebody else wants to bring theirs as well, please do so. So it'll be really exciting to have you out. But it's just to get people into thinking about daytime astronomy a little bit more, because we always take for granted the sun up in the sky, and there's lots to see still at certain times of the year. So that's basically it in a nutshell, but we're going to host it at Glen Lee, and this is the way, for those of you that haven't gone to Glen Lee before, this is where it is. So that's all I have. Thanks, Brent.
Quick question.
Yeah.
That was 10 a.m.
Sorry?
10 a.m.?
10 a.m. Yeah, not 10 p.m. It's 10 p.m. the sun's setting already. Yeah. I hope it is. Is that what p.m.?
No, it's just...
Yeah, you're right here. Oh, sorry, one other thing I forgot to mention. If anybody's new in the club, just feel free to see myself or Brian. We'll have a few of our council members out. Feel free to see me at the break if you have any questions or anything.
Anyways, okay, welcome. This is the June edition of our RASC meeting. I'm Ryan, your president. Great. I'm not on. Dead on it. That's why. On. Off. And testing.
Testing. Okay, here we go.
Okay, so we got quite a lineup today. Of course, I have my intro to do, rather remote. Then we have what's up with Jay Anderson, and then what's new with Danielle, who's here, great. And then we'll have a refreshment break. Then we'll have the main feature of Jay Anderson. I don't know if the title has changed, but we agree upon how the sky moves. And then right after that, for some of you who are, actually we should mention who's new here. You remember? Okay, we've got one. Okay, great. I'm going to point out something towards the end. We have council on board here. You can point this out. We got these little name tags here. And if you want to speak to us, I'll tell you more about it later. And of course, we have the Boston Pizza. And yes, I did schedule it. So I'm not going to mess it up again. All right. Never forget that. All right, what's up? Okay, U of M open house. So again, it's happened this month, the last Wednesday of every month at 7 p.m. Willing permitting, there will be some observing on the top deck. that would be really nice to see. Sometimes they have a really nice 14-inch, I think it is, 14-inch LX200. We only have a 12-inch at Glenlee, but this is nice. What else? Okay, the barbecue's coming up. We had to change the barbecue to July the 12th because of the Bomber game. So if you have any barbecues, we'll make another announcement on the RSC list coming up very shortly, but we do need some barbecues. But what I did last year was I did a little tour at Glenlee because we did some upgrades, and we'll do a little tour again. And time permitting, of course, I'll train some of the new members, kind of get a feel for how to use the new equipment that we have. So that would be interesting. Of course, it's potluck, and of course, yes, it's only for members only. Next, we have Spruce Woods coming up, August. Really nice. I really like this because it's a long weekend. Good time to spend. I can bring my bike if you want to, but I booked time off before and after, so if you have any questions, please see Sylvia, who is here. She's got her hand up right now. So if you have any questions, please see her. You can go to the website to fill out the forms there, but if you register early, you get a discount. And yes, you're going to need a park pass, so please get one. What else? I want to mention about the RSC website. That's something we've been working on. We're going to redesign it, and the navigation part of it is going to be a lot easier. We're going to mention a lot of things, and we'll have an image gallery. Like for example, we'll advertise the open house for the University of Manitoba, and also too, I'll have more information about Glenlee, instruction videos, proper etiquette, how to use the telescope, and all that. But we're still redesigning it, and hopefully we'll have it up and running. Kevin's here, so where's Kevin? No,
McGregor.
McGregor. Oh, okay, sorry. Okay, so how's it coming along with the website?
Slowly but surely.
Sorry, okay, all right. I know that these guys are working hard on it. They are making progress for it. Okay, the GA meeting. This is something I didn't mention last time. It's my fault. But anyways, there's a GA meeting starting yesterday, June the 13th, I believe, right? It goes on to June the 16th. Dennis is our rep, so he's there, meaning that I don't have to attend. But I wouldn't mind actually going. It's in Toronto, York University. So anyways, what else? Telescope loan programs. If you're interested in
Free if you're interested.
too much coffee today. That's my excuse. Anyways, if you're interested in borrowing a telescope that we have, see Abdul. He's got quite a list there. He's right there. And you did bring your...
No, I didn't have the time to bring it this time.
Okay. Well, Dennis is going to get on you. There, sorry. All right. What else? Okay, the survey. What we talked about in our last council meeting, we're going to do a little survey about how well we're doing as a group, as a club. Are we providing enough services? Is there anything else you want to see being done as a club? Events, maybe programs, metro programs, something like that. A survey will be going out. Ed has put it together. He's here right now. And we'll want some feedback from you guys. So once we get that feedback, we'll have another meeting that's separate from our council meeting, and we're going to analyze what everyone's saying. So if you want, for example, I didn't have time to add the YouTube channel. I was on it all this week. We had 55 subscribers, and I saw 2016 J with President at the time, and only one view. Hopefully we can get that number up to 100. So go look for us, RSC Winnipeg, and try to subscribe, and then we can get apparently a better channel or something like that. Anyways, if there's anything else, again, it'll be sent out to members only. So that'll be interesting to see how it turns out. Okay, now, this is not proper in order, but this is the telescope loading program here. Okay, this is just some of the telescope that we have for members. You know, if you're not too sure about buying a telescope or 5 telescopes that we can borrow for 1 month. And it's up to you. This one, this PSC, I really like this PSC. Who has the PSC right now? Does
No one.
No one? Perfect, because we're going to need it for next weekend. Okay. All right.
You're coming, right, Bill? Bill, are you going to it?
Yeah.
Okay, bring it along then, please.
Again next week, right?
Yeah, not this weekend, the following weekend, yeah. I'll make an announcement on the group site.
Yes, okay, great. What else do I have? Well, the Glen Lee Observatory, I'm the director as well. I was going to post, was going to have a members night this Saturday, because the weather doesn't look very promising, but since it was mostly because of the summertime and it's not quite gets dark, it was a golden opportunity to train some of the newer members on how to use the equipment, because it'd be pretty light outside, and you get familiar, because again, some of the equipment, how to use it has changed. We no longer have that nice switch with the dome, it's buttons now. And what's nice about it is you can control it from the warm room, including the LX200s. Okay, if you want the key, come see me. And if you have any questions about Glen Lee, like I do provide training on members night, or any other night that you want to, just come see me, and we can schedule an appointment for you. We have 3 telescopes right now, the LX200, we have a 6-inch Dob and another 6-inch go-to telescope as well. We also have the 16-inch Dob. It's homemade, it's pretty nice, but we have to get that set up. Again, we'll have these telescopes out on members night. All right, a little faster. Okay, just kind of give you an idea of what we have for Glen Lee. This is something I'm trying to work on right now. We have this gyroscope here. It's finally got fitted on the LX200. So it'd be great for beginners. I'll show beginners how to use, how to create your own photography, images. Just the basic, nothing complicated. Free software to use. What else? Okay, like I mentioned here, this whole button thing's kind of like been replaced. Buttons, not that nice switch that we used to have. It's all been simplified. And of course, we were really stocked off with coffee, tea, and water as well. And we have a microwave oven too. I left some popcorn there, so if anyone wants to help themselves, go ahead. I should take a picture of the computer, but I didn't. Okay, as I mentioned, there's no members night this Saturday because of the weather, but it was a little clearer, then I would have something for the new members. I show them. The LX200. Okay, a little training seminar. Okay. Sporting Universe. Dennis is not here. So he's in that GA meeting right now. So if you want to explore the universe, it's a great way to get to know the sky, especially the sky objects that's out there. You have to do some sketching. That's one of the things you have to do. All right, so if you want to contact Dennis, you also just post an RSA list if you're on there. If not, that's his email when I quickly copy it. If not, you can always go to YouTube. We have this recording, and you can always fall back if there's anything you missed. All right, what's next? The Mentor Program, Darren has mentioned that, so come see us. And of course, we have something lined up for next Sunday, a solar event, so it'll be nice. Come see us. What else? The programs, some of the programs that we have lined up for you guys. So it's really designed for the new members. So if you're unfamiliar with how to use the binoculars or digital camera, right? Do we have that? Navigate? No, we don't. Wide field, this is something I would show people, especially the wide field imaging. I'm quite good with that. I love that. That's something I do in Arizona. I do it everywhere that I go to, because you never know what you're going to see. I caught quite a few burners, especially meteorites or meteors exploding in the atmosphere. There's a little shock wave they leave behind. So anyways, all right. Now this is the last slide. This is the council members. For the new members that we have here, we have this to identify us. So if you've got any questions, you wish to approach us during the break, we're more than happy to answer any of your questions. So let's start up with what's up with Jay.
What's up with Jay? Well, I'm 72, married. Part-time. Are we live? Yes. Let's do that 5 and you go. What's up? Not much happening this month. It's quiet. There's no darkness. Hasn't been darkness since the beginning of the month. But there is still a sky out there. So we'll start off with a picture of what it looks like. Now normally I show you what it looks like at 7 o'clock, but of course, so this is the midnight appearance. This is the only time you have any chance at all of seeing anything in the sky. Finally, we're getting the Milky Way coming around to where it's readily observable in the evening, or at least before the wee hours of the morning. So, of course, the Milky Way is best in September, October, when at 9 o'clock in the evening it's dark and it's right there to the south of you. And if we jump ahead a month, you can see that the Milky Way itself moves another 2 hours farther along in the sky, and we get a little closer to our full moon. This particular, it's on 14, I guess they haven't changed the date on that. And the full moon there, but it is July the 14th, actually. Planets. Mercury. Mercury is very nice right now, down low in the evening sky. You have to stay up past 10 and it gets dark enough to see it. I usually find it best to find it in binoculars, and then if you've got a good clean horizon, it's hard to come by in the summer haze, but you can see it by eye quite easily. Once we get to mid-month, it starts to sink into the sun, and it's pretty much gone. First week of July, moving behind the sun. Venus is very prominent in the morning sky, but it is also sinking back toward the sun, so the two of them are kind of going in opposite directions towards the sun. We'll find out about that when I do my little talk later. Mars, interestingly, is near Mercury in the sky, and they actually make a very close approach to each other in a few weeks. And so that'll actually be a nice little photographic target. They're both pretty bright. Mercury is actually brighter than Mars, because Mars is starting to get a rather large distance away from us right now. Jupiter is in the evening, bright up all night. It's that big bright star you see when, as soon as it gets dark enough to look down toward the southeast horizon. And not far behind it, about rising 2 hours later, is Saturn. So the two of them are up and fairly prominent in the sky in the middle of the night and into the morning hours. And Jupiter is currently at opposition, meaning it's directly opposite the sun from us, which means it's also at its closest point to us. So it's quite a large target right now for the Glenn telescope, for instance. If you want to go out there and use that mean, that'd be an excellent telescope for looking at Jupiter and on Saturn. Saturn will be moving into opposition before a month is up. Uranus is it's sort of low in the morning sky, probably pretty hard to see. It's moving away from the sun, so we'll be able to get a better look at it in July. And Neptune is in front of Uranus by about an hour and a half, so it's if you want to take a challenging object, they're just kind of greenish looking stars unless you crank a lot of magnification on the telescope. Some pretty pictures for the month, the 17th and 18th, which is more or less current. Mercury and Mars are passing each other. They're pretty close to each other for the next couple of days. Tonight you could actually go out and get a nice little shot of them. Also tonight the moon is passing by Saturn, and it does it again in a month. It comes around again. And Mars, neither of these are particularly close. There, if you like a picture of the moon in the sky with a bright planet off to one side, then you get it. And because Mars is fading away in brightness, you're probably better off to try it against Saturn. There's an eclipse. I know there's a few of us going, and that's in South America. And then we get to July 3, which I think might be the prettiest event, is pretty low in the evening sky. You're going to want a nice clean atmosphere for that one. I want to talk about astronomical twilight. From the beginning of this month until into the second week of July, there is no formal astronomical darkness in Winnipeg. In other words, astronomical darkness, you have to have the sun 18 degrees below the horizon, and it doesn't get 18 degrees below the horizon at north. It gets to about 16 degrees below the horizon. So for all intents and purposes, astronomy stops for 5 weeks. But it is dark enough to do things in the sky for a couple of hours around the midnight hour, and you have to use standard time, so around 1 o'clock in the morning. We have the solstice on June 21, this time at almost 11 o'clock in the morning. On July 12th, we'll get back into some darkness, and we get 36 minutes of it. So we'll all line up at Glenlee on that date to see if we can share the telescope. Try something challenging. Pluto, we'll have Stan find Pluto for us. The one interesting thing right now, we've seen some evidence of it, is noctilucent clouds. Judy and I have been going out the last couple of nights without much luck, even though there was a good display last night that Sheila was able to see from Collider. Noctilucent clouds are only visible in the summer in Manitoba. They're the highest clouds. They range up to about 85 kilometers above the Earth. So being that high and being relatively transparent, more like cirrus cloud, they're not visible in the daytime. They're only seen when the sun is below the horizon, but still shining on the clouds themselves, which means that it's generally regarded as being visible between the times the sun is between 6 and 16 degrees below the horizon. You usually have to live fairly far north to see them. You don't see them beyond about 60 or even 55 degrees north because the sun is too high underneath the north horizon, and they're still swamped. So they're relatively new discoveries. They've only been known for about a century and a half. And I have seen them from downtown Winnipeg, so it doesn't need a particularly dark sky, but you do have to have a dark sky to get the best pictures of them. Here's one that Sheila sent out last week. Some of you may have seen the little video she had of them that came out today. So they tend to be fibrous clouds, as you see here, and they look a lot like cirrus, but the fact that they're illuminated when the cirrus clouds show up as dark against the horizon tells you that you're looking at noctilucent clouds. If you take time-lapse of them, you'll see there are little waves in the cloud moving. For some reason, this year is particularly good for noctilucent clouds, and they've been seen last week as far south as San Francisco, which is very, very unusual. So here, when can you see them? Well, here's some times. You can sort of pick the middle of it. You'll notice as we get toward the end of June, the amount of time that you can see them in the evening and again in the morning hours is pretty limited. That gets shorter and shorter, and by the end of August, the amount of time that the sun is within the 6 and 16 degree limit is so short that they essentially become invisible. You need temperatures extremely cold to form noctilucent clouds, and the winter temperatures in the mesosphere where they form are actually warmer than the summer temperatures. So you get the cold temperatures in the mesosphere in the summer, and that's how we form those noctilucent clouds. Minus 120 Celsius, typically the temperature needed to form them. And that brings us to the cat.
Next we'll have Danielle. What's new?
Hello, everyone. For those of you that don't know me, my name is Tamia Hood. I'm an instructor here at the University of Manitoba. And today I'll be talking to you a little bit about some recent news in astronomy. So I've selected 3 news stories, and I'm going to work my way from closest to further out in terms of distance from Earth. And so I'll start with a recent result where scientists have found a lot of extra mass or mass distribution on the moon, and what we think that might be. And so I'm going to present this in kind of 2 parts. The first one is that we found the mass, and the second one is that the new Chinese rover has data that corroborates our hypotheses. Next, I'll talk about some new limits imposed on the habitability of exoplanets when we start to consider complexity and requirements for life here on Earth, and some atmospheric chemistry on other planets. And then finally, I'll end with essentially just a pretty picture, but it's a first-time data release of the NICER instrument, which is a soft X-ray instrument that was launched on a SpaceX capsule in 2017. And so it's been taking data for 22 months of the whole sky, and there's a really beautiful image that I'll show you at the end. All right, so let's start. So scientists have found strange mass at the moon's south pole. And so the image here is a topographic image of the dark side of the moon, kind of focused on the south pole of it. So anything that's red is more elevated, and anything that's blue is depressed. And so this large blue circle that you can see, further than the white outline, is the South Pole Aitken Basin, which is thought to be about 4 billion years old. So it's almost as old as the moon itself. The dashed white circle shows the location of the mass anomaly. So there's more mass there than we think there should be. All right. So a mass anomaly, you say, and so they have found a lower limit of 2.0 times 10 to the 18 kilograms extra mass in that basin than there should be. They're not sure how that mass is distributed with depth. They know it's fairly localized within that white dashed circle from the previous slide, but they don't know if it's a thin layer of really, really dense material or a very deep kind of column of material that's just slightly over-dense from the other material in the moon mantle. But either way, it's hypothesized to be either the remnant of the object that created the basin, so some massive collision early in the solar system's history, or a crystallization of some mantle-forming processes. And so this image here is a mosaic made by the Lunar Reconnaissance Orbiter over many of its orbits, and so they're really little, but the golden arrows, the bottom one is the South Pole, and then the one up is the Aitken crater, and so the basin is the dark, depressed area in there. So the measurements were taken by a combination of spacecraft. The first one, as I mentioned earlier, is the Lunar Reconnaissance Orbiters. This is an artist impression of the first one. And then on your left, right? One day I'll get that right the first time. Is the other pair of instruments. This is the GRAIL mission, the Gravity Recovery and Interior Laboratory. And so the spacecraft are named Ebb and Flow, respectively. Yeah, I thought that was pretty good too. And so here again we have an artist's rendition where the left half of the moon is just the moon, and then the right half of the moon is the density or gravity that's being measured from the surface. And so these spacecraft send microwave signals to each other, and then based on the tug, differential tug of gravity on each of them, they can kind of reconstruct the mass distribution of the moon interior to that using spherical harmonics and some measurements. So here's what they did. So they took the topographical measurements from the Lunar Reconnaissance Orbiter, which are shown here on the left. And so you'll recognize the basin in blue, outlined in black this time, and then again the mass anomaly in the white dashed line. And so again, the red is crust material that's more elevated, and the blue is crust material that's been depressed or lowered down. And then on the right-hand side are measurements from the GRAIL spacecraft. And so in this case, the red has higher gravity and the blue has lower gravity. And so you can see that there are a lot of similarities. A lot of craters are in blue for the GRAIL. but not all of them. But the anomaly is still quite blue. And so here, I had no part in this, none. The moon's topography is important, and so they can use that to inference what the mass distribution must be. And so we know that there's a crust on the top and then a mantle underneath. It's hypothesized that there's a kind of an upper mantle and a lower mantle. And so when they look at the crust, they can take measurements of its composition and its height and kind of infer some thickness. And so they can guesstimate, essentially, the mass or the weight of the crust based on its composition and thickness. And then from that, they can start to make inferences about the density of the mantle. And so the moon, for it to kind of stay robust, has to be able to support the weight of the crust without flexing too much. And so by combining the measurements of the topography and the gravity, here they have some mass anomalies. And so now, again, you have the same angle from the moon, and here we have a computer simulation of interpreting the data of over-densities and under-densities. And so now the mass anomaly, still in the dashed line, but now in gray, you can see that it's very strongly over-dense. So it's way denser than the rest of the moon. And so if you assume that this mass distribution is fairly thin, then you get something that's really, really dense under the crust. And if you assume that it's more distributed, then you can have a more nuanced density change for a larger depth. But here they've assumed, for geological reasons that I am not an expert on, that it tends to be homogeneous, the mantle tends to be homogeneous beyond a certain depth. So that's what they found. So these measurements, regardless of how they're distributed, are what they're found. Okay, so now there are two main theories for what could have caused all of this. The first on the left is the remnant of an impactor, which I alluded to at the beginning. And so we know that in the early solar system, collisions were happening a lot. The moon probably resulted from a collision of something very massive with the Earth. Things are very heavily cratered. So we know that collisions happened very frequently. And so usually in astronomy, when we can't explain something, we assume it's a collision. Venus is orbiting weird, collision. Uranus is rolling, probably a collision. I get a lot more laughs from my first year students. Just saying. But yeah, so possibly a collision. And so if there was a collision with something that was metal-rich and very dense, it was its own differentiated body on its way to being a planet, and it rammed into the moon, then maybe some of that core didn't sink all the way down to the core of the moon. So if for some reason those cores didn't fuse, then you would have this very localized, more dense region kind of in the moon's mantle. And so that's depicted here. And so they've run simulations for this, and if you had a 95-kilometer diameter iron-nickel core striking the moon in its infancy, then you could get a mass distribution kind of like this. The second, less exciting, not less exciting, less dramatic or catastrophic source could be that the moon still does have a molten core, very thin. In the past, it probably had a lot more, and so there would be some convection, and so if you had some material differentiation or elemental differentiation in that convection cycle, and it kind of froze, then you might get kind of an overdensity in the downwelling. And so if you have that for certain chemicals, then you can have an anomaly like this that would end up being really deep. They've also run simulations for this, and so depending on the papers that you read, they have different levels of disagreement. So this is something that will still need to be looked into. But some models say that something the size of the anomaly is too large for this effect to explain, but that's not agreed on. Okay, so now for the support of the collision hypothesis, the Chinese spacecraft, Chang'e 4, I'm not quite sure how to pronounce that, landed. It's the only spacecraft to have landed on the dark side of the moon, which is where the SPA basin is located. So this graph shows on the left the near side of the moon that we can see, and all of the landers on it. The blue dots are American missions, the red dots are the Soviet Union missions, and then the purple are China. And so China, so far, is the only country to have landed on the far side of the moon. And so its spacecraft is the only dot on the far side shown up here on the right. And so it's landed right in the SPA basin. It has a rover called U-22 that has been trucking along and taking spectroscopic observations, and so it's looking at the chemical composition of the rock. And it's inferred the presence, from its measurements, of the presence of olivine and low calcium pyroxene. And so these minerals are minerals that we think are in the mantle of the moon. And so it's consistent with a big collision to have something slam into the moon and have some of the mantle material spray out into this basin. And now the rover is measuring it. Okay, so why do we care? So the interior structure of the moon hasn't changed a lot. So the moon, unlike the Earth, is very close to us. It's one of the things that's easiest to get to. It's a rocky body. It formed very close to us on solar system scales. But it isn't eroded away by weather or tectonic activity. And so everything that's ever happened to the moon, you can probably still see hints of now. And so it gives us a really good indication or hints at the long history of the early solar system all the way up until today. And so the young moon was a magma ocean, mostly molten, and then it became chemically stratified with heavier elements in the center, lighter ones up at the top, further out. And so the core forms first with dense mafic materials which contain magnesium and iron, such as olivine and low calcium pyroxene crystallize at the ocean's base. So you start with the magma, the core forms, and then the mantle kind of becomes ocean-like and starts crystallizing. And then the crust at the top forms next. And then you get less dense materials, such as aluminum silicate, floats to the surface and forms a highland crust composed mainly of calcium-rich plagioclades. And then finally the mantle crystallizes last. So it's kind of the last thing to form. And so if you were to have a really large collision kind of as it's forming, then the body, the core, could still be there. Any questions about the moon?
Why didn't we, I mean, I know you may not have seen anything about it, but I mean, I know they've had like seismic testing and so on since the Apollo missions. Was there never any inference of this feature maybe earlier on? And then now the data's kind of supported it because they have better resolution? Or any ideas? Or did you see anything like that?
Just in case everybody didn't hear, the question was, there's been seismic measurements on the moon, especially since the Apollo missions. I'm not sure where those instruments are placed, but if we have seismic instruments on the near side of the moon, those are still very far from the backside, and I'm not sure how well or how sensitive they are so that you could measure something like that, especially since it's static. It's not, it's not like an earthquake that propagates. It would just be a simple mass. So I think that might be tough to measure. Yeah, Michelle?
I'm just wondering, I heard that like the origin of the moon comes from an impact of the Earth again, and from this globular ring, which then forms two separate moons, which later fuse together. Would that be a result of that?
Cool. So in case people didn't hear, Michelle said the moon was formed by a giant collision with Earth, and then it formed a ring with two kind of proto-moons that then fused together.
Yes, there was a bigger one and a smaller one. It sounds like maybe that supports that theory.
Yeah, it might support that theory. I don't know enough about it. Yeah, there was another question back here.
So does that offset mass cause any wobbling of the moon, or changes to the way it's going, or it changes to the way it rotates, speeds, etc.?
I'm not sure, to be honest. I don't know. Yeah, sorry.
I think
just had it locked. I don't know if it creates like a little wobble, but you probably wouldn't. Yeah.
Just to see, with cratering on the moon, is there any indication of when this event might have happened by looking at cratering? Would have been before the moon was solidified and on the surface? So there would be no indication of by cratering on impact?
Right, so the cratering, I think once the moon was solid, or at least most of it was solid, the craters stay, right? You don't have a molten.
So would this happen before that?
Well, they think that this is what caused the basin.
Oh, okay.
So they think that the whole SPA basin was caused by this impact, and that the core, which is smaller than the whole crater, the basin crater, would be kind of lodged inside. So all of this would have happened about 4 billion years ago. Yeah.
How big is the basin and the size of it?
Oh boy, okay. The basin, I want to say, is about 1/5 of the circumference of the moon, which is maybe 2,000 kilometers.
Such confidence.
Yeah, confidence with remembering numbers off the top of my head is really my strong suit. I think that's about right. I can look it up for you later. And then the actual mass anomaly is less than that by about 1/4, I think. Yeah.
2 half questions.
Oh boy.
Trying to make it clear. First one is, and actually this is a good diagram here. So it actually has formed a depression. Is that correct? Like, because it's so heavy, it's just like a heavy object sitting in a liquid, and it's trying to sink towards the center. Is that correct?
My understanding from what I've read is that the collision caused a depression,
Okay.
and then the mass still sits within that.
Okay. Okay. And then second half question is, this is probably a really dumb question.
Yes, it should be.
The 2 space probes you had up there in the second one, I forgot the name of it. What happens with the probe as it's going over the higher density area? Does it go in a higher altitude naturally, or a lower altitude because of the additional gravity? Like, I'm assuming that as it's orbiting, its orbital distance from the center of the moon would vary over the higher gravity. So does it get closer then, or does it go out?
That's a really good question, and one that I was anticipating and really desperately tried to find the answer to, and wasn't able to. My intuition is that the spacecraft would get pulled down by regions of higher gravity, would get attracted a little bit more strongly. I mean, these are going to be really minute changes. There's
So that's how it would actually measure the gravitational field then, I guess, based on that.
I think so. Okay. I'll stay afterwards if anybody has more questions. But for now, we'll move on to the limits of habitability on exoplanets. And so here is a schematic of a star with lots of planets around it, and this is the Goldilocks problem all over again. The ones that are too close are too hot, the ones that are too far away are too cold. But somewhere in the middle is just right, and liquid water can exist. And a lot of astrobiology and exoplanet science really is quite curious about finding these planets that would have the right temperature range to have liquid water exist on their surface. And so the habitable zone is defined almost unanimously as where liquid water might exist on the surface of a planet. And so this new study said, well, that might be enough for simple single-celled organisms, just water. But for complex life, for things with mitochondria or cellular components or multi-cell organisms like humans or bacteria, just water might not be enough. What effects will things like atmospheric chemistry and pH have on them? And so this study looked into those possibilities. And so what it did, it said, okay, well, let's take a look at the range of life here on Earth. What are the ranges of temperatures and pHs and pressures that complex life can live in? And then where could we find those? What constraints can we put on exoplanets given the type of life that we find on Earth? And so they start by saying, okay, well, we can tell from fossil records that the diversity of life really proliferated with an increase in oxygen. And so not only is liquid water important, but so is oxygen. And the more oxygen there is in an atmosphere, the more likely you are to have metabolic complex life. Okay, but if you have oxygen and you have water, you almost certainly have some carbon, you're going to have carbon dioxide and carbon monoxide, and both of those are going to have an impact on the atmosphere and on the life that can exist. And so they did a bunch of simulations, and I have plots from the paper here. The paper is cited at the bottom. And so anytime you see an S, they're looking at solar fluxes or brightness of the star relative to the sun. So here we have most of our exoplanets are found around faint stars because planets are easier to find around faint stars. So it's biased towards that a little bit, and those faint stars tend to be cool. And so here, for the plot furthest to the left, there's stellar brightness relative to the sun on the y-axis, and then the carbon dioxide pressure in the atmosphere on the outer edge of the habitability zone, so where liquid water could exist. And so then here, the different colored bars are the temperatures of those stars. So for different temperature stars and different brightnesses, you would get different levels of carbon dioxide. And the more carbon dioxide you have, it's a greenhouse gas, it actually keeps the planet warmer. So it extends your habitability zone a little bit, because it keeps your atmosphere warmer, and so you can have liquid water further out than people have thought so far. So first of all, the carbon dioxide extends the habitability zone by a little bit. The plot in the middle is the effective temperature at the surface of the star, plotted against OHZ as the outer habitability zone. And this is the pressure, again, of carbon dioxide. And you can see that the temperature of different stellar types, spectral types, are plotted here. And then finally, on the plot on the right, again, we have the pressure of carbon dioxide. And then on the top axis are they've assumed calcium on the planet. There are a lot of assumptions that go into these studies. But they've assumed saturated dissolved calcium ions in the water, which affects the acidity of the oceans, which affects how life can form. And so here in so the gray solid bar is kind of historically where the Earth has been. The white boxes represent kind of the ideal range for each of these types of animals. So humans are in one spot, sponges have a much wider range, squid have a very different range. And then for different spectral stellar types, you have the different colored boxes. And so you can see that they're playing around in a lot of parameters for stellar type, temperature, and they're making a lot of assumptions about chemistry. Okay, and so this is a plot that exoplanet scientists like a lot. So there's the temperature of the surface of the star, so spectral type of the star, versus brightness. So it's your kind of sideways Hertzsprung-Russell. And then here you have the dots are the planets that have been found. And then the two solid lines are the kind of edges of the habitability zone. And so you can see that the Earth is right on the inside edge near the top. And then a lot of the other exoplanets that have been found are kind of splayed around. And so then the three different kind of transparency levels of color are the three different concentrations of carbon dioxide in the atmosphere. So for low amounts of carbon dioxide, the habitability zone is small, and then it moves out as you allow for higher and higher concentrations of carbon dioxide. But if you have carbon dioxide and you have it close to these low-mass stars tend to be very magnetically active and release a lot of UV and a lot of X-ray. And so the photochemistry that happens is that carbon dioxide turns into carbon monoxide, which is toxic. And so you can build up toxic gases, which are unfit for complex life. And so here they're accounting for predicted levels of certain toxic gases, and that narrows the safe zone by at least half. And in some cases, it eliminates it altogether. So here in blue, the blue band is kind of habitable for complex life. And again, you have the temperature of the star relative to how bright it is. And then the planets are in gray and black dots. So anything in blue is safely habitable for complex life. Anything in like the mustard yellow is toxic to carbon dioxide. Anything in orange or red is toxic with carbon monoxide. And so if you start considering that different chemical reactions in the atmospheres, and you start to really narrow down where complex life might exist. All right, so consequences and caveats. So no safe zone at all exists for certain stars, including two of the sun's nearest neighbors, Proxima Centauri and TRAPPIST-1, which has 7 planets around it, I think. And so the type and intensity of ultraviolet radiation that these cooler and dimmer stars emit can lead to high concentrations of carbon monoxide, which is a deadly gas. Carbon monoxide binds to hemoglobin in animal blood, which is the compound that transports oxygen through the body. And then again, although the team concluded recently that microbial biospheres may be able to thrive on a planet with abundant carbon monoxide. So this whole study is really based on life that's developed on Earth. I don't find it unreasonable to think that if you start with a different type of chemical soup at the beginning, you might evolve life that has different tolerances than your own. But it's still interesting to think about how physiologically, chemically, and astrophysically these things can interplay. Okay. Any questions about that?
The four-color graph showing habitability, does that mean Earth is on the very edge of their habitability range?
It looks like it.
Raises the question about the central nature of Earth as a habitable range.
Yeah.
Wasn't it Arthur C. Clarke who said that if an alien species came past Earth, they'd look at it and go, oh my god, it's so toxic and corrosive with oxygen, no life could live there?
I know this isn't necessarily your area of expertise, I don't know, but I was going to say, do you know of any studies, like they always use Earth as a model, and I understand why, but when you start looking at these dimmer stars, like let's say you did get plant life at some point, even the hemoglobin in animals and the chlorophyll is going to be based on a different element, right? Instead of magnesium, you might have something else, and same thing with hemoglobin, you might have copper or something. So, do you know of any studies that are trying to emulate conditions that might exist in these, that might kind of support some of this data? I don't know if this has.
Yeah, no, it's a really good question. And astrobiology is not my field of expertise. And Michelle is welcome to chime in if she would like, or has different opinions. My kind of coming up through my studies and kind of hearing about it tangentially, my biggest annoyance is that it seemed to rely so heavily on life on Earth. Why would we expect chemistry to happen? You know, if things are developing at very different pressures and very different temperatures, why would we expect the same things? I've learned a little bit more chemistry since then, and so I know that there was a study that made a big splash a while ago. I think they had cyanide-based life forms. They thought they had found them in a salty lake in California. It ended up being an incorrect result. At first, people thought, hey, maybe it doesn't have to look like life on Earth. I think one of the main reasons people really focus on liquid water, other than it's been so important on Earth, is that as a solvent, it's unparalleled because it's polarized, and so it really allows for a lot more chemical reactions. And so the chemical reactions could happen a lot more rapidly in liquid water when they're dissolved than they would in any other solution. And so that makes liquid water a pretty good candidate for finding evolution or complex molecules.
I'm not disputing that. I'm saying with the alternate chemistry with regards to
Yeah.
you know, because you can have still aqueous chemistry going on with other elements, as you know, organic analysis is an example, right? That are still supported in the aqueous chemistry. Not only that, when you look at these magnetic active stars with UV, you could have a higher concentration of things like photolite, like CO would start to photolize as well. You might even have atmospheres that almost resemble Titan as an example. Maybe a little different, but you know, you start getting those kind of chemistries that become much more complex. So that would absorb a lot of the excess UV and then shift things back again. Like I said, there's a lot of questions to consider, and I know that's a pretty big question I have. I'm sorry.
Yeah, I think it's probably easiest to look for life that looks kind of like what we've already know, but I think it might be limiting. Yeah.
That wasn't a fair question. I'm sorry.
It's okay. It's an interesting one, though. It's a valid one. Okay, and then the last topic is the Neutron Star Interior Composition Explorer, or NICER. And so this is an instrument that is mounted on the International Space Station. It was launched up in 2017 by a Dragon probe, a SpaceX. And it observed soft X-rays, and it maneuvers in a way that's very clever. It looks at about 4 objects per Earth orbit, which is an hour and a half long. And so this thing is constantly moving around, looking around. And it's observing soft X-rays, and it's mapping out pulsars, so dead stars with strong magnetic fields, in the galaxy. And so this image that I'm showing you is an all-sky map, and so this is everywhere. And so everywhere that's bright, especially the really bright things, are pulsars. And so you can see the Cygnus loop and the Crab Nebula. If they don't jump out at you directly, I don't blame you. I've got a labeled one next. And so you can see some of the streaks are tracks that the NICER instrument traces more frequently. And so some of the filamentary structure, especially the long swooping ones, is an artifact of the way that NICER takes data. But still, you can get a good map of all of these magnetically very intense stars. And so this is the labeled image. So Cygnus loop here is up and to the left. The Vela, which is a young pulsar, is kind of down in the middle. And so this is a first release of some of the data. And we'll leave you now. Yeah, Michelle?
Galaxy with that weird, funny shape on
Which
trying to
one?
understand the
Black
projection.
Orient.
Like I see.
So this is an all-sky survey. So the galaxy is going to be...
It's got a weird shape, right?
Yeah, I think sometimes for all-sky surveys, depending on the projection they use, sometimes it's this weird, like half circle. Well, full circle, but it's like swoopy. It's like an ibex.
I'm thinking it's that this, that's why.
This
Yeah.
guy?
Yeah,
Yeah.
that's what I'm thinking.
Yeah.
Swoopy.
Swoopy. Okay.
Yeah, that's what I was thinking.
No more questions. That's it.
All right, we'll take a short break here. We'll take a short break. We'll convene 10 after 9. And of course, any questions?
And the same ones aren't there anymore. They've moved. And the planet moved. And the sun moves in an annual cycle, and a 1,000-year cycle, 2,000-year cycle, 2,000,000-year cycle. Well, I'm not going to get into all that. We're just going to talk about how does the sky move. way does it turn? Looking from the North Pole, is it turning clockwise or counterclockwise? I see you're all thinking, which way does it go? Which way do the stars rise? From that side. So which way does the Earth turn? That way? That way? I'm going to tell you things about it. And which way do the stars move? When you're in your annual orbit, you look at the stars like I show you month to month. They've moved about 2 hours every month. In other words, the equivalent of waiting 2 hours and see what stars are rising. I'm going to put this up again when we're done because it's important. It's a little bit of a tour de force or tour de farce, depending on how well this works today. So I'm going to be popping in and out of. Thought it was anyway. One of the problems with using Starry Night is that Starry Night has a few bugs. And one of them is that it doesn't follow all of the Microsoft convention. Okay, here we are. This is June 8th. It's only because I started it on June 8th. The evening sky, time is up here, getting on towards 6. This is the ecliptic, this line. It says February, March, April. It marks the position of the sun at those times of year. The sun moves along the ecliptic. At least apparently the sun moves along the ecliptic. And I have to overcome some of the bugs. So let's just take a look. We've got how it moves day by day. Where is the sun right now? Well, at 5 in the evening, it should be somewhere up in the sky, and I think I forgot to turn it on, so I'll just look at that. So what you see is the sunset. Now
You're in the morning right now, Jay.
yes, so you're right. 6 a.m. There we go. I'm going to leave the title on, but I'll let you know what it is. So Starry Night goes bananas if I give it the command to go forward. So I'm stepping time forward. So I'm just going to go on a day-by-day basis here.
Is that daylight saving?
So where sun sets
I like daylight saving.
and darkness comes, and we see the planets. And this is going by pretty quickly. You can watch the years in here. This is at a day-by-day motion, so you're looking at the sun approximately the same time over a 2-year period. And it went up and came back down as it followed the seasons, going higher in the summer and lower in the winter. We go back to where we were before. And we go ahead. It's behaving itself. So here we have the stars rising at night, and we'll just go by day. And you can see the moon moving across the sky, and there it goes again, and there it goes again, as each month goes by. There's a couple of things you should notice about this that we'll bring up later on, but the moon didn't follow the ecliptic. depth of the stars, just so that. All right, now let's go hour by hour. And we'll go turn over to the sunset side and watch the sunset. And there's the moon. This is a couple of days ago. Because we're going hour by hour, it gets fairly quick, so let's just dial in, say, 10 minutes. Oh, well, I thought I got a 10 in there. So when I go ahead 10 minutes, to watch the Milky Way rising on the eastern side. Which way is the Earth turning? Is it going toward the Milky Way or away from the Milky Way? Toward the Milky Way. Obviously, if the Milky Way is coming this way, the Earth has to be turning that way. It's turning, when you look at it from the north, counterclockwise. A lot of people think that the Earth turns the other way, that it's carrying the stars with it. It turns into the stars. Look at this ecliptic. It's at an angle to the sky. So the direction that the sky is turning, as you go along in the day, the ecliptic forms a bigger and bigger angle with this time of year, the ecliptic is relatively low in the sky. We'll get into that later. What I mostly want you to know is the way the stars themselves move from day to day as they rise and set. And if I zoom out, this little feature here is an attempt to make this thing look like there's a reflection. And as you watch the ecliptic, it comes to night, and there it is low, and in the daytime it's high again. And that will become important later on. Nice lake of the woods scene here. Well, that's pretty straightforward. So let's take a look at step 2. Here we are. The star is overhead at night, and I've drawn this star up in the corner. I don't know if it does appear. And of course, that's at a more or less infinite distance. But on day 1, the Earth is actually going counterclockwise in its orbit around the Sun. All the planets go counterclockwise, so they rotate. Other planets rotate differently. The Earth rotates counterclockwise and goes around the Sun counterclockwise. So on day 1, I'm that little orange dot, and I look out and I see this star in this direction. Now, if the Earth didn't move 24 hours later, I'd look out and the star would be in that direction. But I move along my orbit. And so when day 2 comes, I've gone a little bit around the curve, and the star comes up a little bit quicker than it did, because I don't have to rotate back to the same position, because the Earth has moved me partway toward that position. And so my star comes up slightly earlier. So how much? 365 days in a year, 360 degrees in a circle. So the Earth moves 1 degree, approximately, every day, which means that that star rises 1 degree sooner in angular motion. So here's the math. 24 hours, 60 minutes in each hour, 1/360th of a circle. The star rises 4 minutes earlier every night. And so, over the course of a year, and think about it, if you were stationary and the Earth didn't rotate but kept one face toward the sun, as you went around the sun, every time you came to night, you'd be looking out in a different direction. And so, the motion annually around the sun mimics the rotation of the Earth. Of course, at night, on Earth, you only look at this side of the sky. You don't see the other side because the sun's in it. But when you're just going around the Earth every night over a 365-day period, you would see the entire sky that's visible in your hemisphere going by. Well, we have a way to stop that. Here's a diagram that shows you every night you're looking out in a different direction as you go around in the orbit. And so you would see the entire sky go by in a year. And we're lucky because we rotate. We don't get stuck with the same view every night. If we didn't rotate, though, we wouldn't need equatorial drives. We could just stick a telescope up. But nothing. You could just put it on a tripod, take an hour-long exposure. Now, we can change that. We can say, well, what would it look like if we kept time by the stars? We didn't worry about noon till noon. We said, we'll keep time every time this star out here is at this angle to us. And so sometimes that star would be in the darkness, and other times it would be at dawn, and other times it would be in the middle of the day. It's called sidereal time, stellar time. So what does it look like? I wrote it up. So here we are. We just watched the star. This is Arcturus. You should know how to find that. We've talked about it. There's the dipper, so you're arcing to Arcturus. Now, sidereal time, Arcturus should maintain itself stationary. But now, our time is going to go backwards 4 minutes every day, as far as everything else is concerned. So let's see how, I'll just do this. I'm going one day at a time. One sidereal. Now, not much is happening because the stars don't move. But, oh, the sun's coming up, though. And you can watch the time changing, it's going later each day, but the time of day for each one of them is different. And so that is what would happen if you kept sidereal time. We'll let it run automatically here. And then we get back into nighttime again. And there is Arcturus still sitting here in the sky in the same place that it was before. Well, sidereal time is not very useful, but it used to be. It used to be a way of finding things in the sky. But what you can use sidereal time for, and we'll show you later on, is watching the motion of other things in the sky and how they move with respect to the stars. So if anything in this scene was moving, the stars would be stationary. You would see that object moving, and that could very well be one of the planets, a comet, any one of the various things that stay in orbit or are in orbit with us. Where am I here? There we go. Put this guy back up again. We'll make use of sidereal time occasionally. I want to talk about the ecliptic and the equator. We've mentioned both of them. And on this diagram here, I show the position of the ecliptic right here, and the position of the equator at this particular time of year, December the 12th, actually. So, in December the 12th, the sun is close to its most southerly point, and the ecliptic at the same time is close to its most southerly point. Now, the position of the equator changes as you go through the year. Here we have a diagram in the winter at the top. This is where you are, standing in the earth, and overhead is straight up from the surface of the earth. And you're in winter. The equator is at this angle, and the sun is low. So you would see it underneath the equator, same as the diagram I showed you in the previous slide. So here we have the equator and the ecliptic maybe down underneath it. Move into the summer, we know the sun is high, where in here the equator is taking the daylight side, is still the same angle toward the equator because you're on a fixed point on the earth, and the position of the equator in the sky, the projection into the stars of our equator doesn't change. But the sun has now come higher up. And so we would expect, since the sun is following the ecliptic, that it's going to take this annual motion, and the ecliptic is also going to take this annual motion up and down in the sky. Let's see if this works. No, it doesn't work. So one of the bugs of Starry Night is that it ignores a few Microsoft conventions. So let's have a look at this. Here we have it. One of the things I wanted to demonstrate from this is that the planets and the moon to some extent tend to line up along the ecliptic. We'll see that a little more exactly, but it's because most of the planets in the solar system orbit more or less in the same plane around the sun, so they would follow the sun's track across the sky. And when you go out these days and see Jupiter and Saturn go down in the sky, then you know that they are in the sort of winter ecliptic. Now, I've got a sidereal day on here. So the stars aren't going to change as we go. Let's just stop that a bit. And one of the things I want you to know when we get back into the darkness is the motion of these planets along the ecliptic. And you'll notice some kind of strange behaviors of the planets while we're here at this time, just to sort of see how things work. Well, let's go and take a look at this at a one-day interval now. We won't keep the stars fixed in the sky. We're up September 2020. I know that's not going to bug you too much. And since we're going day, I'll just do it like this. It takes too long. And notice how the ecliptic rises up. Here we into March, the ecliptic. When you think about it, you're on a tilted Earth. You're rotating at this angle and you're orbiting at this angle. So depending on where you are, that ecliptic, as I showed you in the diagram, is going to change its position in the sky. If the ecliptic and the equator, if we rotated exactly perpendicular to our orbit, the ecliptic and the equator would be coincident. But this has a lot of implications for us when it comes into where the planets are. So if Jupiter and Saturn were along here, then you would have them much higher in the sky at night. But because they're not there at this time, well, they got a 12-year orbit of Jupiter, so you got to wait 6 more years before it's moved far enough along the ecliptic that it's in the higher part of the ecliptic, the winter ecliptic. Because if you go here to daylight and noon, no, we're not there yet. Let's keep going backwards. I'm going by day. I want to go by hour. So it's 6 p.m. Go back a couple hours. This is our summer ecliptic. Not very visible, but there it is. There's. It's high up in the sky because the sun is very far north right now. But that means the other side of the ecliptic is very low in the sky. So when we have the ecliptic high in the summer and the sun up high, we have the midnight ecliptic is very low. And so what you really want is planets that make their opposition in the winter. We now have the opposition to Jupiter in the summer. If it was in the winter, it would the sun ecliptic on the daylight side would be low, and the ecliptic on the night side, where we want to watch the stars, would be high. So on a night-by-night basis, you watch. On a night-by-night basis, you watch the ecliptic rising and falling in the sky. And on one side, it's showing you where the sun is, and on the other side, it's showing you where the nighttime planets are. It's like a disc, a wobbly disc, that one side is high, one side is low as you go in your orbit around the sun and during the course of the year. And so it helps to explain why Jupiter is at opposition but so low in the sky for us. It's because it's summer. And you just have to wait 5 more years and Jupiter will have moved slowly in its orbit until it gets to the other side of the ecliptic, and then it will be high in the sky in the winter months. And Saturn will take even longer to get there, and but things like Mars and the other planets, they get there much more quickly. So Mars, one time of the year, you only have to wait about a year and a bit before Mars moves into the high side of its orbit. Of course, because the sun is following the ecliptic, then it has a bearing on the pattern that the sun follows during the course of the year. It's going to rise and fall with the ecliptic. So let's load up. Look at that. Now a lot of you have seen pictures of the analemma. Just make sure. So I'm going to take a 5-day step, and we're starting on June 1, so the sun is almost at its most northerly point. And we're going to go ahead in 5-day steps, and it's going to trace out its orbit. That is not definitely what I wanted to do. As I say, it's one of the little bugs that's built into Starry Night. If you hit the go button and don't make a time step forward, it goes bananas. It'll eventually settle down in about the year 2150. So here we are watching the sun. This is 1:30 in the afternoon, which is close to local noon time. And we've seen these analemmas before. This is the pattern that the sun follows in the course of a year. And if you set up a camera and take a picture once interesting that if I do it manually first, so this is how our sun moves. There you go. Ignore all the other ones. This figure 8 that we get is called an analemma, and you've seen people publish pictures where they took a camera in one spot, they have lots of clear skies, and once a week they take a picture and trace out the analemma. And the north to south motion on this sun is caused by the changing position of the ecliptic, which in turn is dependent on the fact that the Earth's equator is tilted with respect to the plane of its orbit. And the back and forth motion is caused by changes in the speed of the Earth as it goes around in its orbit. Some places it's a little fast, other places it's a little slow, because our orbit is not exactly circular. And so we have little changes in the speed as we go around. I'm kind of getting distracted here. I'm just going to run this analemma once more the right way. And so here we are coming down to our most southerly part of December 31. It's a little bit past it. And June 21. And over the period of millennia, these will change so that the analemma will get flatter, it'll move to different times of the year when you get maximum low. We won't worry about the climate change. You'll notice that this analemma is not straight up and down. It would be if I was exactly at solar noon. I'm a little bit off of it because I'm looking here at 12:02 with daylight time, and I should be closer to 1 o'clock. Well, what happens if we look at this in the morning? So we'll take the sun, March the 5th, I just picked that date. And here it is, as the sun is rising in the morning. I've made it high enough so that it's visible for the entire year, but if you went for part of a year, and we'll just go ahead on a 6-day step. And the sun does pretty much the same thing, goes north, where June 21 reaches its maximum, comes back down until it reaches its minimum. Yeah, I hit the wrong button. Reload it up again. I knew this was going to be a problem, but I should write these guys and say, hey, look, picture programming. Okay, so let's just do this again. Instead of watching the sun, I'll watch where the cursor is until I get round to the bottom again. You'll notice that when we get down into the winter months, the sky's it's pretty close to just after sunset. Let's take a look at this. We're going to zoom in a little bit. Right here is the bottom of the analemma. It says the 24th of December. That's actually put the little mark. There's no way to get away from it. So probably where the hand is the bottom of this analemma. It's not as visible on your screen as mine, and I hope you can see it coming down here. But what we should do is turn off the sunlight. Right here, hardly visible, is the lowest point of the analemma, which would represent the latest sunrise. So even though the sun reaches its minimum point here, its most southerly declination, it's not the latest sunrise for us. And it's because this analemma tilts over in the morning and in the evening that when you go look at the charts and say, well, you know, we should have the shortest night on the 21st, the shortest day on the 21st. We should have the latest sunrise, which is what's showing up here, and we should have the earliest sunset. And it's not there. The latest sunrise comes a little bit after. And so it's because of the tilt of the Earth and the way the sun makes this figure 8 pattern that those things, it's still the shortest night because what you lose on one side you gain on the other. And the analemma depends a little bit on latitude as well. Here's the sun, this is Belém in Brazil, which is very close to the equator. Well, because you're in the equator, your sun follows a somewhat different pattern. It's still got the analemma, but now, because you're now sitting in the center of the Earth's rotational plane, the analemma is tilted over. And you can see that the ecliptic is almost straight up down. So it's the sun is going north and south. And of course, if you were to take this and move it up to noon, it would be straight up and down. Well, what is the latest sunrise in Belém? You have 2 times of the year, once here and once over here. This is not, you actually have to go slightly off of the equator to get 2 perfectly aligned sunrises and sunsets. So this is one of the things. Of course, in the tropics, the sun is going on each side of the equator when you watch it moving across the sky. So you can look at this analemma and the annual pattern of the sun in the sky and trace out some of the more mysterious things. And it's not an explanation, the fact that the analemma is leaning over a little bit in the morning is not the cause of a late or an early sunrise. It's simply the fact that the tilt of our orbit gives us these early and late sunrises and the speed at which our sun is moving in its path around in orbit. Well, I wanted to take a view from the North Pole a little bit. Have you ever read a book called Arctic Sky? It's the story about the Inuit vision or view of the sky. And you sort of think, well, in the north, they're not going to see all of the stars because half the year the sun's up the whole time. And yet, I think there's some interesting things that happen in the north that might change your mind about that a little bit. Okay. I'll get these guys up and running, yeah. So here we have our North Pole with the North Star right here. It says international waters. It turns out when I type in North Star as a position, it has a default. And the default is easier to accept than to fight it. So we go 7 days at a time. Here we are getting into September. The sun is sinking in the north. And so all night long, the stars just go around and around and around. But you see all of them when you're in the middle of winter because it never gets daylight. And halfway around, you lose all of them. Because the sun, here it is. We'll just turn that up. There's the sun rising and showing you what it's, the only part of it, I don't know where this mountain came from in the North Pole. Quite a few Edgar Rice Burroughs. So all you're seeing is the top of the bowling ball from the North Pole. And I'm about to lead an expedition there to find this place because I haven't put Shangri-La or whatever it is they call it. You can get a little bit. One thing is, I think I started with it. Anyway, who knows? So that's just a little, you can do some interesting astronomy. If you wanted to, for instance, when the moon is above the ecliptic in the winter, you can get moonlight that continues all night long. In fact, Judy and I were in Norway both watching aurora, and it was very unusual to see the aurora and the moon essentially on top of each other because we're so used to having the moon in the south and the aurora in the north. It turned out to be a peculiarly part of the moon's orbit that to get away from the Earth a bit. We're going to look at the inner planets right now. I don't want you to get out of my way. This is my problem here. Well, you've seen this every time in high school. You have 3 planets in orbit here: Mercury, Venus, and the Earth. Does the Earth qualify as an inner planet? I guess it depends on whether you're on the daylight side or the night side. So, first of all, notice that Mercury's orbit is not centered on the Sun. It's quite off-centered. Venus, on the other hand, seems to be pretty much centered, and the Earth is, well, if it's centered, then Venus isn't, or vice versa. But it means that there's a changing distance between the planet and the Sun. And we mentioned that because it's what modulates the speed of the planets. I'm going to hope this works. It does. And of course, the closer you are to the Sun, the faster your orbit. But think about what's happening here. Here we are in the Earth going around, and Mercury's scooting in periodically, and then we become visible again. It passes between us and the Sun, and then it passes behind the Sun. And the only times we're going to see it is when it's on one side of or the other of the Sun. And this is when Mercury is either in the morning before the sun rises or in the afternoon after the sun is set. And from our point of view, Venus is much the same. But we're all going around in the same direction. If we were going in the opposite direction, they go past us very quickly, but we're actually following along beside them. Not very at the same speed, but you can see how long it takes Venus to catch up to us, and we'll see it beside the sun. And then after it passes, it goes more quickly, it seems, behind the sun. And Mercury is sort of the same. We see Mercury here, but it's scooting so quickly it gets ahead of us very, very rapidly. And so in this diagram is some evidence of the fact that Venus is probably visible for a much longer time from the Earth than Mercury would be, because our speeds in orbit are closer to each other. And there's actually a bit of a difference. You know, Venus is still visible when it's on the other side of the sun. Here we are passing. So when it gets onto the other side of the sun, it's still visible to us, but now it's going in the opposite direction in the sky from our perspective. And so what we want to do is actually put together a lot of this into the way that it might appear in the sky itself. So we're going to take a look at the motions of Venus right now, which I guess I already know that. So now Venus is a morning object or an evening object. But actually sometimes it's a middle of the night object too, although it's pretty low in the sky when that happens. What I'm going to do is trace out why Venus has the patterns that it does. Venus in the evening. What have I got? I got October the 1st this year. Here's Venus behind our mountains. I guess I could make it flat, but I won't. It's a very interesting scene. So at the moment, see what we can get out of there. At the moment, I'm just going to step ahead on a day-by-day basis. And we watch Venus sinking down beneath this. Put it flat horizon here somewhere. 7 p.m. on October the 20th. So remember, we're going day by day. So what it's telling you is that each day Venus sinks a little bit lower below the horizon, but it's falling below the horizon much more slowly than the stars, and it barely gets below and then starts back up again. So here in December, Venus is climbing higher and higher in the sky, so it barely disappeared below the horizon when it came back up again. Very strange sort of behavior. You kind of expect Venus to disappear and go into the morning sky, and it did very briefly when it was below that horizon. We got to deal with the sun here, but Venus is getting higher and higher in the sky. Now we could change this by making it a little later, just to sort of get it back into the darkness. But I don't want to do that so you can see how it's moving. And then it seems to slow down. Well, obviously Venus has got its own characteristics in orbit, so let's go back to the start on this again. Take a look. And this time, I got back to my, we'll fix that again. Flat horizon. So now I'm going to turn on the track to see how Venus actually moves in our sky. Now let's see if this works on this button. So, see, eventually it'll start working on its own. It's kind of got to accelerate it. So I don't know what it is, but I have to run it manually. It does that on all of my computers. All right, so we're going to go day by day. We're going to put back that flat horizon so we can see everything. Okay, and then let's see how it goes. And I think we will turn on the local path, trace a bit. And periodically it'll put a time in here and try not to lose my way on this arrow. So here we come. Probably should make this a couple of days. How about if we do that? We can move a little more quickly under those circumstances. Let's say 3 days. It'll be a little more jagged. So this is the way we see Venus in our own sky. Now it does get into the daylight hours. As I said, we could just change the time. And eventually makes a big broad loop and finally gets down to, and then here's the sun, of course. So now it's gone behind the sun and is on the opposite side. So you'd have to catch that in the morning before the sun rises, and Venus would be a morning object at that time. Well, it's kind of an oddball pattern. It rises very high, and it's probably close to 35 or 40 degrees high here. I could have stopped it at the time and looked to see what that was. It was a bit of a mystery at the start as to why Venus would have that kind of a rising up really high and then not. So this time what we'll do is we'll turn on the local path and we'll turn on its orbit. Because two things are happening. Here's the orbit of Venus right now, which you can see as this curve here. And the sun is down here, so this is just looking at the orbit of Venus around the sun. So this is October, and the Earth is moving in its orbit, and the ecliptic, the path of the sun itself is sinking down toward its minimum. And so what you have is the track of Venus is made up of two things. It's made up of the Earth's motion around the sun, where it's following Venus, but not quite at the same speed, and Venus's own orbit around the sun. So now, again, we'll put this up to a 4-day motion, and then we'll just watch the way Venus goes. So it's staying on its orbit. Here it comes, following its orbit up into the sky, sitting, but now the motion of the Earth is making that position in the orbit. And so when it gets to here, Venus is at its its most easterly point in its orbit. We call that its eastern elongation. And at that point, it's, in this case, 47 degrees high, more than halfway up in the sky. Those are glorious times to watch Venus. You have to go and maybe go a little later so that the sun is set. And of course, when I do that, I get an immediate 1-hour motion of Venus, but they put it back where it was. They excused the little zigzag. And then Venus continues to follow its orbit. And then it scoots very, very quickly, because at that point Venus is going behind the sun and it's in the opposite direction that the Earth. So all of a sudden we're passing each other like this instead of like this. And so on the backside of the sun it moves quickly. So it rises very slowly over a period of months until it's halfway up in the sky, and then it scoots back around the sun and goes into the backside of its orbit, goes behind the sun and becomes a morning object at that point. So what you're seeing then is a combination of the impact of the Earth's orbit and the impact of Venus in its orbit. And Mercury is much the same, but it's much closer to the sun, so it's not quite as dominant. Don't look at Mars now. Mars is interesting. Mars has got the most eccentric orbit, so it's definitely much closer to the sun than it is that time in its orbit than it is over here or over in here. But it also, here's the Earth's orbit, so there are times when it's very close to the Earth in its orbit, and other times when they're in opposition, and it's quite a long way away. And we're pretty familiar with that. So when we look at this in Starry Night, oh, I see. One thing I wanted to talk about is Venus in its orbit. So we'll look at Venus from up above. This is above the Earth's orbit, 2.5 astronomical units, so 2.5 times as far as the sun. Here's the sun, and here's Venus's orbit. And I'm going to do a 7-day stint. Now, the problem with this, here's Venus following in its orbit. And remember, we're looking at this from above. And you could watch the orbit of the sun. You can see Venus is going around it. And it makes this nice little loop. Be careful here, because it's getting away from me. This is called the Pentagram Venus. And after 8 years, it follows exactly along behind the ones that it's done previously. There you can see it doubling up there. And so we've doubled the line in here. Every 8 years, Venus appears at the same place in the sky because it has this kind of orbital resonance with the Earth, that 8 Earth years is equal to, I don't know how many Venus years is in this, but this is something that's been known since the days of the Babylonians. Astrologers are just, they go crazy over this kind of thing because obviously there's some kind of sign written in the sky here. We see it from the Earth as Venus simply returning to the same place, which is why transits of Venus are 8 years apart, 2004, 2012. I think it's one of those interesting patterns that results when you start examining the sky in this sort of obscure points of view that you can get when you have a planetarium program like this. Anyway, I'll go back to Mars and take a look at Mars, and this is pretty straightforward. We're just going to go around in the orbit. And of course here, Mars is outward bound from the Earth, so when we're going in the same direction, side by side, we can stay in that position for quite a long time, although the separation from us gets pretty far. But Mars is still on this side of the sun for us, and it's only when it gets to here. So we can actually go for a very long extended period of time. You might have noticed that Mars has been something we've been talking about for months, always seems to be in the southeast horizon because we're following along in parallel to it in orbit, and then it finally flipped over to being on the other side of the sun. So each time we go by, eventually we get to the point where Earth and Mars are passing each other at the narrowest part of the orbit, and that way we get a much bigger view of Mars. In this particular example, it's about as far away from us as it can get. So it takes a number of years, 2.5 years per orbit, and so you're looking at 10 or 12 or more years in the future before Earth and Mars will pass each other at a favorable opposition. But the eccentric orbit of Mars was actually quite important to Kepler in being able to derive the motions. So we'll stop that. We're just about out of time here, so I want to do just one or more interesting groups. Let's see what we got here. Open up. You ever wondered what the Earth looks like from the moon? Nah, nobody ever does. So where is the Earth? This is the Earth. Oh, that's Jupiter. Here's the Earth right here. Well, the moon keeps the same face toward the Earth, so what's the Earth's orbit around the moon look, or what's the Earth's orbit look like from the moon? And there it is. The north-south motion and the east-west motion are the librations in the moon's orbit. It's not moving at the same speed all the time, so the left to right position of the Earth changes. And it's tilted a little bit, so the north to south position of the Earth's orbit changes. And this makes complete sense, but you never really think of what's the Earth's orbit look like from the moon. From the Earth, the moon's orbit is, it's going around the sky along with everybody else. It changes its phases, and if you could look closely at this, you'd see that the Earth is changing its phases too at the same time. It's just going round and round and round, and we can move on to other places in the world or in the universe too, and have a look at here I wanted to look at one of the characteristics of, I don't know why I'm in the Central African Republic. Because I wanted a place near the equator. Now I'm just going to hit this button and see whether it behaves itself or not. Cannot get this program to do what it's supposed to do. So we'll have to do it the hard way. Now, you'll notice I'm using sidereal, well, you probably didn't, I'm using sidereal days here, so the stars are going to remain fixed, but we can watch the planets in their motion. And there they are. Remember, it's a sidereal day, so this is actually the opposite direction. And then they turn and they go backwards, which is their normal. There's a very nice December 21, 2020. It's going to be really nice. Now, we'll forget about the sun. But these are what are called prograde and retrograde motions. This is a prograde motion here. Now see how Saturn has now turned and gone back? Here's Jupiter now following it in retrograde. And these are caused by us passing them. So they're like cars. As we pass Jupiter, we see it against the stars this way, and as we go in front of it, it's against the stars that way. So it appears like it goes backward for a time. And this retrograde motion is quite interesting and quite characteristic of outer planets versus inner planets. So here we are going retrograde here, and they stop. And these are important, what are called stationary points, especially if you happen to be an astrologer. Notice that these two planets are not right on the ecliptic at this point. So here they are now prograde going the way they should along with all of the stars, although they're not at the same group. And then next year comes by and we go back into retrograde again. So these stationary points where it stops and then goes back and stops and goes forward are just a manifestation of the orbits of planets that are exterior to us. And you'll see when you look in your handbook that those stationary points in retrograde motion are mentioned. And the last one I want to talk about is this little guy. I don't know if I dare take, let's not chant. So we got the Earth over here, but that's okay, that's not what we're looking at. Well, we're sitting on Mercury here. Melville crater, it says. And what we're really watching is the sun. And here's the sun rising. Keep an eye on the date up here. It's rising. The days are going by, the 13th, the 14th, the 15th, the 16th. As the sun rises on, oh, Mercury has an 88-day orbit. And it turns 3 times in every 2 or 2 times in every 3. But if you watch this, after a while, the sun stops rising. It's not quite so you can't put sidereal time in this because it has sidereal time for the Earth, not for Mercury. But for a very brief period, it actually goes backward very slightly and then continues on in its orbit. Once again, I think it's going to behave itself there. Slowing down, backward slightly, and then forward again. And here we are up in December. We started 1st of October. A very interesting planet for meet you at noon. Well, you want the first noon or the second noon? They're a day apart or 3 days apart. So anyway, I hope you got an idea how things move in the sky. There's some wicked movements in it, and some of them are pretty ordinary. But now you should have a better feeling for why Venus is where it is, and why it's high in the sky, why Mercury is sometimes really nicely placed and why other times when it's not, and how the ecliptic affects what season you see these various things in the sky, especially the planets. So thank you very much.
And that'll conclude this